In this section, we will continue talking about confidence intervals, and specifically, we will revisit constructing a confidence interval to estimate a population mean. But this time, we will look at how do we do this if sigma, the population standard deviation, is not known. So let's go ahead and dive in here. In order to explore this concept, we have to tweak the formula that we looked at last time using a different distribution. So we're going to learn about the properties of what we call the student's t distribution, and then we will look at constructing confidence intervals for a population mean when the population standard deviation is unknown. So let's start off by talking about the student's t distribution. Now, in the previous section, we went over the process for deriving the formula for a confidence interval using the sampling distribution for the sample mean. And the formula we ended up with is this: sample mean plus or minus the margin of error. And the margin of error was the z critical value times the standard error. And the standard error is sigma over the square root of n. And this is the formula we came up with last time, right? And in order to use this formula, you have to know what sigma is. Normally we don't, because sigma is the population standard deviation. And typically, we don't have access to the entire population. So in order to derive this formula, we used the sampling distribution for the sample mean. And as long as the right conditions are met, what we know is that the sampling distribution for the sample mean follows a normal distribution, right? And we ended up using this formula for the z-score, x bar minus mu, oopsies, I apologize there, over sigma over square root of n. And this quantity follows a normal distribution. Now, if you don't know what sigma is, then what you have to do is replace sigma with the sample standard deviation, right? Now, like we said, it's rare that we would know the value of sigma while needing to estimate the value of mu, right? Sigma is the population standard deviation, and most of the time we don't have access to the entire population. So actually it's more common that sigma is unknown. If we don't know the value of sigma, we may replace it with the sample standard deviation, and we use the letter S to represent the sample standard deviation. However, it gets a little bit more complicated than that, because once you take the z-score formula and replace sigma with S, this quantity here no longer, it's still a random variable, but it is no longer normally distributed. Okay? It does not have a normal distribution. And so that means that we cannot use the same methods that we looked at in the previous section for finding the critical values for our confidence interval. This quantity right here follows a distribution that's referred to as the student's t distribution. So we have to look at this new distribution in order to be able to modify our formula to find the critical values. It's also going to require utilizing a different chart, as we'll see in a few minutes. But first of all, let's just cover some of the basic properties of the student's t distribution. There's actually lots of different student's t distributions, and they're all distinguished by a quantity which is referred to as the degrees of freedom. When using the student's t distribution to construct a confidence interval for a population mean, the number of degrees of freedom is simply defined as 1 less than the sample size. So it's the sample size minus 1. Now, a student's t distribution, at first glance, it actually has a lot of similarities to a normal distribution. It is still unimodal and symmetric and bell-shaped. However, students' t distributions are more spread out. As you can kind of see, the dotted line, the solid line curve is the standard normal curve. And the dotted line curves represent different students' t distributions with different degrees of freedom. Okay? So what you see is that these students' t curves, the tails tend to stay a little higher, right? They take longer to come down low, like the normal curve. So they tend to be a bit more spread out, and they don't peak as high. Okay. The reason for this is because S, the sample standard deviation on the average, tends to be a little bit smaller than sigma. And also S is a random variable, whereas sigma is a constant value. So both of those factors have the effect of increasing the spread of the resulting distribution curve. We see this tendency more when the number of degrees of freedom is small. Okay, so like here, this one right here, this is a student's t distribution curve that corresponds to 1 degree of freedom. That would mean a sample size of 2, right? Since the degrees of freedom is defined as 1 less than the sample size. This blue dotted line curve is a student's t distribution curve with 4 degrees of freedom. That would be a sample size of 5, and you can see it peaks a little higher, the tails come a little lower. The red dotted line curve is a student's t distribution curve with 10 degrees of freedom. That would be a sample size of 11. You can see it peaks even yet a little higher. The tails come a little bit lower, right? So as the number of degrees of freedom increases, that also corresponds to a larger sample size, right? What that tends to do is that the sample standard deviation will become a closer and closer approximation to sigma. And so the student's t distribution will start to look more and more like a normal distribution. And in fact, if you have a sufficiently large sample size, you can just treat your distribution curve as a normal distribution. The cutoff there is, I believe it's above a sample size of about 200 or higher. But if your sample size is anything lower than that, then we have to treat this as a completely different distribution curve. We cannot use the normal curve tables to find our critical values. So the table that we would use to find the critical values, it's in your appendix. It's table A3. It's just a one-page table. That the alpha over 2 notation, which we introduced last time, it still applies in this case, right? The only difference is that the distribution curve is no longer a normal curve. It's a student's t distribution curve, right? So instead of using the letter z to represent the random variable, we use the letter t, right? So t alpha over 2 has an area of alpha over 2 to the right. Negative t alpha over 2 has an area of alpha over 2 to the left. 1 minus alpha is the area in the middle, and that is the area that corresponds to our desired level of confidence. I'm just going to flip over real quick. This shows you a brief snapshot of a little bit of the table. I want to pull up the full table, which is right here. So you got a diagram at the top there of your student's t-curve. So the way the table is structured, you have degrees of freedom on the left here, and then the numbers in the main body of the table are your critical values. This row at the top, labeled area in right tail, we will not use that at all for confidence intervals. When we get to talking about hypothesis testing, we'll use that portion of the table. For confidence intervals, if you go down to the bottom of the table, you'll see down here confidence level. All right, so what you would do if you want to find the critical value, you would start with your sample size. Let's say your sample size is 20. Then you would use your sample size to find your desired degrees of freedom, which is 1 less than your sample size, right? So the degrees of freedom is 19. So here's the row corresponding to 19 degrees of freedom. And then you would find the number in that row corresponding to your desired level of confidence, right? Let's say you have 19 degrees of freedom and you want 95% confidence, then your critical value would be 2.093. That's the number that you would multiply by your standard error in order to find your margin of error. Now, if you come down to the bottom of the table, you see your percentages, and then directly above your percentages, there's a row that's labeled Z, right? What this is saying is that once your degrees of freedom gets more than 200, that basically means your sample size is now sufficiently large that you can just revert back to using the numbers from the standard normal curve for your critical values. And in fact, if you recall in the previous section, we looked at that small table for finding critical values for the most common levels of confidence. That table is essentially the last two rows of this table, right? These numbers right here are the critical values. Oops, sorry about that. The numbers in this row labeled Z, those are the critical values that were in that small table that we looked at last time, right? Which means that if you're doing the homework, say from section 8.1, and you need to find one of those critical values, you can also use this chart, just refer to this row, right? But if your sample size or your degrees of freedom is 200 or less, then you would have to use the other method for finding one of these other values for your critical values. Okay, let's come back over here. And let's kind of look at an example here. Let's say a simple random sample of size 10 is drawn from a normal population. We want to find the critical value T alpha over 2 for a 95% confidence interval. So because the sample size is 10, that means the number of degrees of freedom is 9. So we would go to the table and we would find the row corresponding to 9 degrees of freedom. And then we would move across that row until we find the number in the column corresponding to 95% at the bottom. So where that row and that column meet, we find the number 2.262. That would be our critical value. Now, you'll find that the table will not have every single degree of freedom value. If we flip back over to the table, you'll see that it has every number from 1 up to 40. But once we get to 40, then it jumps to 50, jumps to 60, jumps to 80, jumps to 100, jumps to 200, right? So for the bigger numbers, it tends to skip. So what do you do if say, your degrees of freedom is something like 45 or 44, a number that does not show up here? These are the rules that we would follow. Okay. If the desired number of degrees of freedom isn't listed in the table, follow one of these two rules. If the desired number is less than 200, use the next smaller number in the table, right? So if your desired degrees of freedom is, say, 46, use the row corresponding to 40, because that's the next smaller number. If the desired number is greater than 200, we've already kind of alluded to this one, then we can use the Z value found in the last row of table A3, or just revert back to the standard normal curve table, because at that point, it just means your sample size is big enough that we can just treat our distribution curve as a normal curve at that point. Okay. Assumptions that have to be met in order for this to work. Pretty much the same assumptions we've been making for the central limit theorem in the previous section. The sample has to be a simple random sample, and we have to either have a large sample greater than 30, or it has to be based off of a population that is approximately normal. We'll find that it's fairly common to have sample sizes smaller than 30 when using this approach. And so if you need to check that second assumption, an easy way to do that is to draw a quick dot plot or box plot, but dot plots are a little simpler. And you want to just check to see if that dot plot looks relatively symmetric. You don't want to see any evidence of strong skew or anything like that. But if the dots are pretty evenly spread out, then it would be reasonable to assume that the population is approximately normal. So that's one way you can check that second assumption. So let's go through some examples where we actually construct some confidence intervals using this method. This is the step-by-step procedure that we will do, and notice it looks pretty similar to the method we introduced in section 8.1. We're just tweaking the formula a little bit to use the student's t-distribution instead of the normal distribution. Okay? So first of all, we have to know the sample mean and the sample standard deviation. Some problems, those values might be given. In other problems, you might just be given the raw data and you might need to calculate those values, right? But somehow you need to obtain those numbers. Step 2, find the number of degrees of freedom by subtracting 1 from the sample size, and then find the critical value, and you can do that by referring to the chart table A3, like we just looked at. Step 3, compute the standard error by taking the sample standard deviation and dividing by the square root of the sample size, and then multiply it by the critical value that you obtained from the chart in step 2, and that gives you the margin of error. And then construct the confidence interval by taking the margin of error and adding and subtracting it to the sample mean, and then finally interpret the result. So here's our first example. A food chemist analyzed the calorie content for a popular type of chocolate cookie. The following are the numbers of calories in a sample of 8 cookies. And we are asked to find a 98% confidence interval for the mean number of calories in this type of cookie. And notice that the only data that's given are those 8 numbers, right? So one of the first steps is to check the assumptions. Generally, unless it specifically says otherwise, we can assume that the sample is a simple random sample. But the sample size is pretty small. Sample size of only 8, that's much smaller than 30. So we should check our second assumption, which we can do by just putting together a quick dot plot, which you see there. And if you look at the dot plot, we've got 8 dots. They're fairly evenly spread out. They're not like all concentrated at one side or something like that. There's no evidence of strong skew, no outliers. So that's good enough to satisfy that assumption, so we can proceed. Now we will need to have the sample mean and the sample standard deviation. The sample mean is found by adding up those 8 numbers and dividing by 8. And if we did that, we would get 115.375. The sample standard deviation can be computed using the method we discussed back in chapter 3, right? That's where we covered the procedure for calculating the sample standard deviation. You can do it by hand, or you can use technology to find that. But when you calculate it, you'll find it to be 2.8253 when you round it to 4 decimal places. Next, we will go to the table to find the critical value. Because our sample size is 8, that means our degrees of freedom is 7. So we'll go to the table, we'll find the row corresponding to 7 degrees of freedom, and then find the number in that row corresponding to 98% confidence. And that number is 2.998. And then next, we'll take that critical value and multiply it by the standard error. Again, the standard error is S, the sample standard deviation, divided by the square root of the sample size, square root of 8. When we do that calculation, we get a margin of error of 2.9947. And then the margin of error gets both subtracted and added to the sample mean. And the final result is our confidence interval. And we can conclude by saying we are 98% confident that the mean number of calories per cookie is somewhere between 112.4 and 118.4. So that's the process for constructing a a confidence interval using this method. Let's look at another example. In this one, we have a sample of 123 people aged 18 through 22, and they reported that the number of hours they spent on the internet in an average week. And the sample mean was 8.2 hours. The sample standard deviation was 9.84 hours, right? So in this example, the sample mean and the sample standard deviation are provided. If we assume this is a simple random sample from the population of all people aged 18 through 22 in the US, we want to construct a 95% confidence interval for mu, the population mean number of hours per week spent on the internet by people aged 18 through 22 in the US. So, we're told that we have a simple random sample. The sample size is larger than 30, right? It's 123. So our assumptions are met. So we can proceed. The sample mean and the sample standard deviation are given, so we do not need to calculate those values. So we can just jump to the step of finding our critical value from the chart. The sample size is 123, which means that our desired degrees of freedom is 122. But 122 does not appear on the table, so what we'll do is we'll use the next smaller value in the table, which is 100. And we'll take the number in that row that corresponds to 95% confidence, and we'll find that number is 1.984. So that's the number we will use for our critical value. Then we take the critical value and we multiply it by the standard error. Sample standard deviation divided by the square root of the sample size, and we get a margin of error of about 1.7603. And then we get the sample mean, and we add and subtract the margin of error, and we get our final result. Now we can conclude by saying we are 95% confident that the mean number of hours per week spent on the internet by people aged 18 to 22 years old is between 6.44 hours and 9.96 hours. Okay, so now what we'll do is we'll go over how to construct these intervals using a TI-84 calculator, and we'll revisit the same two examples, but this time use the calculator to do them. So the function you would want to use for this would be the function called t-interval. And again, it's in the tests menu. If you recall, in section 8.1, we used the function labeled z-interval. This time, we'll use the next one down, the one labeled t-interval. And again, just to review, to access this menu, you press the Stat button, and then you highlight the word tests. And that will get you to the tests menu, and t-interval is the 8th one down. And then once you select that, you'll have two options for input, either data or stats. Data is what you would choose if you're just given the raw data. So that would be like the first example we looked at to estimate the calorie count for the cookies, right? All we were given were the calorie counts for 8 cookies. So we would use data for our input in that case. Stats would be what you would use if the sample mean and the sample standard deviation are provided for you, and that was the case in the second example we looked at. Okay, so we'll go over both so you have an example of how to use both input options. Let's start with this one, the first one, right? The calorie content for the cookies. And our goal is to find a 98% confidence interval. So check assumptions, right? We've done all this. So if you're doing an example like this one, the first step you need to do is actually to open up your list editor. Which again, you do that by pressing the Stat button and then highlighting the word edit, pressing enter, and it brings up your list editor. And then in list L1, you would want to type in your raw data. In this case, the 8 numbers that are given in our sample. Just type those numbers into L1. After you've typed the numbers in to L1, then you press the Stat button again, highlight the word tests, go down to T-interval, press Enter, and then you want to make sure the word data is entered. And then you should see a screen like this. In front of the word list, it should have an L1. Frequency should default to 1. You shouldn't need to change that. C level, put in your desired confidence level, which is 98%. So we would put in 0.98. Highlight the word calculate, and it's going to give you this result, right? The confidence interval. These are the two numbers, the lower and the upper endpoint in your confidence interval, separated by a comma. And then it also gives you your sample mean, sample standard deviation, and sample size, right? So that's a fairly nice way of finding these confidence intervals. Example 2, right? In this one, the sample mean and the sample standard deviation were given, and we are asked to construct a 95% confidence interval. Assumptions are met. So this time we do not need to use the list editor. We just go straight to the T-interval function. For input, we make sure that the word stats is highlighted, and then we just type in the relevant data, right? Type in 8.2 for the sample mean, 9.84 for the sample standard deviation, 123 for the sample size, 0.95 for the confidence level. Highlight the word calculate, press enter, and it gives you your confidence interval there, your sample mean, sample standard deviation, sample size, and so on. Okay? So that is how you would do it with your TI-84. And again, if you have any questions about your calculator, if you're having trouble with it, please reach out to me, and I would be happy to assist you with that. So this wraps up our discussion on finding a confidence interval for a population mean, right? In this section, we looked at the properties of the student's t-distribution, and how to find the critical values and how to construct and interpret confidence intervals. In the next section, we will go over how to do a confidence interval to estimate a population proportion. So that will be the next topic. Thank you for watching this video.